Recording in progress.
Morning, everyone.
Morning.
Doing good today? You doing well?
Yeah, doing well today.
Yeah. Me too. Pretty good day. I always like doing this class on Thursdays because it's a good wrap up to the week. My other course, the discrete structures course, is a little, it's more theory, it's more abstract, and so this is a good, practical stuff to do on a Thursday. Plus, I have a lot of fun. Well, while we wait for a couple more people to show up, I guess I can ask the other people how they're doing. Oh, I can't get them out of their shell this morning. Well, are there any questions about the material so far? Some of you are probably thinking, it's a balancing act for me as an instructor. Like, how fast do I go? Do I just tear through this material really fast, or do I kind of pace it out so that people who are still getting up to speed have some time to get synchronized with the rest of us? So I kind of like mixing things up a little bit of the stuff that's kind of keeping pace with the book, and then some extra stuff. So I'll see if there's a good mix today. Well, when we left off last time, we were writing this program, if you recall. This was about calculating the width or the diagonal of a television if you knew its width. And we did it two different ways. We did it once using the Pythagorean theorem, and we did it also with some trig functions, cosines and tangents and so forth. And then we had taken those functions or those pieces of code to do those calculations and moved them into their own functions. One of them was called trig_diag. It takes in the width of the television and returns a double with the diagonal, and also one called pythag_diag that also takes in the width of the television and returns a double as well. And then we had to put those functions, or we wanted to put those functions down at the bottom of our program. And in order to do that, we have to leave behind these function prototypes up at the top to let the compiler know that there is going to be a function called trig_diag and pythag_diag. The bodies of those functions will come later, but this is enough information for the compiler to be able to call the function and get a return value back from it. See, when the compiler needs to call a function, if you recall, we looked at the assembly code, all it puts down in there is an instruction that says call and then the name of the function. But before it does that, it has to place the arguments or the inputs to that function kind of in some spots where that function can then find them. So it has to do a little preparatory work, and then it calls the function, and then when the function returns back to that part of the program, the return value is also sitting in a place where the program can get access to it. So when you call a function, those are the only things it needs to know. It needs to know what are the parameters, what are the types of the parameters, and what order do they have to go in so they can put those things in the right spots. Then it just simply calls the function, and when the function returns, the return value is sitting in a spot where it can get access to it. That's all it needs to know. It doesn't have to know how the function works. It doesn't have to know anything about the code of the function, because all it does is inserts an instruction that says call that function, and that function assumes that the parameters have been set up in the correct order. So that's why a function prototype works. It has just enough information for the compiler to be able to construct the call to that function, and it doesn't have to know anything about how the function actually works. Okay, so that's where we left off last time. Now, since I am I'm looking at the screen here. Is it because of my connection, or is everybody's screen like cutting out when I project himself on the main window? It could be because the screen is so big, and so I remember last semester another student had this same problem where it was kind of stuttery, and I'm going to have to ask him what he did to solve that problem. There was something he could do on his end that would make that problem go away, but it was also something I could do on my end. So let me try that. Zoom has two modes that it can operate in. I'm sorry, I went off track a little bit here because I was distracted. I saw the chat message here, and so this may solve the problem for some of you. Zoom has two modes it can operate in. One is the standard mode that we're in right now, which is most of the time what's going on the screen is either there's a talking head on the screen or there's just slides like a PowerPoint presentation. There's not a whole lot going on the screen. And that means that my computer doesn't have to send a whole lot of data to the Zoom servers. All it really has to do is just send what's changing, and there's not a whole lot changing. Now, if I'm just doing a presentation, really not a whole lot is changing. Most of the time it's just a static image, and once in a while it flips to another slide. When I'm doing my head on the screen, a lot more is changing because I'm waving my hand around and my head is moving. And so the amount of data that is allocated to sending the video information may be less than the amount of data is actually needed. And so it compensates by just lowering the frame rate. Now, if I was to play a video, you'd probably see it really stutter. And you've probably had this experience maybe in some of your other online courses where the teacher plays a video and it like updates only once a second or so. It's really kind of annoying. And so there's a menu in Zoom where you can say optimize screen share for video clip, and that will boost the data rate coming out of Zoom and allow it to have a much smoother video. And so that's what I just did. I just enabled that menu item, and now hopefully that will make things a little better for you. So let me know if that fixed the problem. Yes, apparently it did fix it. So I need to boost that video rate coming out of here. And it's also because we get to do because we pay for our Zoom service, we get to do HD video, so you're getting like the full, 1080p experience instead of the 480p that the free accounts get. Anyway, little side note there. So it looks like I've fixed that problem. Okay, so when we left off last time, we had moved those calculations into their own functions. But now, as a TV installer, I realized that I might need to use those functions in other places. Maybe I have another program to do something else with televisions, and I need those functions to be able to be used in another program. So what I want to do is move those functions into their own file so they're separated from the main. So we're going to do that next. I'm going to create a new file, and I'm going to call this a diag.c. And in that file, I'm going to put the two functions. Oops. It's hard to scroll this, but there we go. So I'm going to cut that out and paste it into diag.c. Okay, and then in my tv.c, I don't have those functions. In fact, for the time being, I'm going to take out these function prototypes as well. So all I have in tv.c is just the main, and all I have in diag.c is just the functions. Let me save both of those. And then to compile them together, I can issue the clang command, but I can list out both the C programs. And then the compiler is going to take both the C programs, compile them, and put them together, and then make one executable. But I've got a bunch of warnings here. Now, the first thing that I should note here is that these are all warnings. They're not errors. So it did actually compile the program, and we now have a working program. So warnings are kind of like error messages, but all they are is just notices to you that something suspicious is happening, but the compiler is going to let it go. But let's dig into this a little bit and figure out what exactly is happening here. So the same warning is appearing 4 different times, and the error code or the warning message is implicit declaration of function whatever. What does that mean? What does implicit declaration mean? So let's play the role of the compiler. So this is generated by the tv.c file. So let's look in here. And there's a call in here to trig diag. Now remember that when the compiler sees a function call, it doesn't actually have the body of the code. So it doesn't know how that function is actually going to work. But based upon the context that it sees here, it can take a guess as to how that function would be declared. So let's see what if we're playing the role of the compiler, what we can ascertain about this function based just upon what we see here. So again, the compiler is in this headspace where it's like, okay, I see a call to trig diag, but I don't know anything about that function, so let me guess as to how it's going to be declared. So if the programmer had put the function prototype in there, what would it have looked like? So what do we know about the function based upon what we see here? Well, certainly we know its name. Let me write down the function declaration here. So certainly we know it's called trig diag. But what else do we know about it?
We know that it returns a double and it takes a single argument that's a double.
Good. So it takes a single argument, and we know that it returns a double. How do you know it returns a double? Let me just clarify that. What do you see here on this statement that would give you the hint that it returns a double?
The type of the variable that we're assigning the value to.
Very good. So the compiler can see clearly that this variable called diag is a double, so that means that trig diag probably returns a double. Now, it could return an integer, and we could assign it to a double, but we're guessing how it might be declared. So it probably returns a double, and it probably takes one single parameter. Do we know anything about that parameter?
We could assume that it's a double because of the type that width is.
Good. So we can see this variable called width, and we see the declaration of width up here. Oh, actually, width is declared to be an integer. So trig diag probably takes an integer as a parameter. And we don't know its variable name. We don't know the name of the parameter, but we're pretty sure it's an integer, and that's based upon the fact that width is an integer. Okay, so that's probably what the function declaration or the function prototype looks like. That's called an implicit declaration. An explicit declaration where we, the programmer, actually write it out. But an implicit declaration is where the compiler guesses what it is. Same thing's happening here for the atan function, and that's in the diag.c file. So over here we've got atan, and again, it doesn't know what the actual declaration of this, but it can guess. It can guess that atan takes in a double, and it returns a double. Same thing for cosine. It takes in a double, and it returns a double. And also for square root, it's going to guess that it returns a double, and it takes in a double because w and h are also doubles. So these are all implicit declarations. They're all guesses as to how the function is actually declared. But the reason why these are warnings is because when it actually goes and puts together all of the files, it realizes, oh, actually my guesses were correct. Okay, so when it goes and finds trig diag, it goes, okay, I guessed it returned a double and it took in an integer. But it actually returns a double and takes in a double. But that's okay because I can pass in an integer to a function that takes in a double and it will just expand it out to fit. So that's not a problem. If the roles had been reversed and I had guessed it took in a double but it actually takes in an integer, that probably would have generated an error because my guess was now completely wrong and it wouldn't work. But I can pass in an integer to a function that takes in a double and it will work just fine. So that's why I let this one slide. This is its guess was slightly incorrect, but at least the guess was compatible with what it actually was. So later on the function goes, oh, here's how the function actually was declared. Did that match my guess? Was it good enough? If it was, I'll just let it slide with a warning. If it was incompatible, if my guess was not correct, then it will generate an error and say this implicit declaration does not match the way it was actually declared. All right, so I wanted to go through all of that to explain what this warning or error message means. And I guess the big takeaway there is it means that you did not tell the compiler exactly how that function was supposed to be declared. It had to guess. And sometimes the guess is correct, and sometimes the guess is incorrect. If the guess is correct or close enough, it'll generate a warning. If it's incorrect, it'll generate an error. So how do we fix this? How do we explicitly declare what the functions are? Well, we did that last time. We have to put in the function prototypes. So in the tv.c file, we've got a call to trig diag, so we should put in the function prototype for that function. Let's go ahead and do that. And when you're putting in function prototypes, all that matters is the name of the function, the return type, and the type of the parameters. The names of the parameters actually don't matter. It's the types that are important. So I can literally put the word something here, or I can put X, or I can put ABC. It doesn't matter as long as the types are correct. But I'm going to go ahead and, for completeness, go ahead and match what it actually is. Let me look over here. It's W. Okay, and then over in diag.c, we had some warnings about atan, cosine, and square root, and so I could put in the function prototypes for those as well. And I have to put them in this file, diag.c, because this is where the functions are being called. I can't, I could put them into tv.c, but it wouldn't do any good because those functions, those math functions, are not being called from this program, or this file. So there's two ways I could put in these function prototypes. I could either just write them out. I'm only using 3 of them. Or I could include the math.h header file, which itself has those function prototypes in it. So let me go ahead and do that. I'll just use include math.h, and then that'll bring in all the function prototypes for those math functions. Okay, I'll save both of these, and let's try compiling it again. And you can see now there are no warnings, because now the compiler has all the information it needs to be able to compile the program without generating any warnings. Let's go ahead and try to run it. Looks pretty good. Width of 34 inches results in a diagonal of 39 inches. So I just talked for about 15 minutes. Are there any questions from you at this point? No? Okay, so let me refresh your memory about what we talked about last time, which was these stages of compilation. You start with your C source file. It goes through the preprocessor, whose job is to handle things like those preprocessor directives that start with the hash mark. Those are things like includes, and they also include defines. Defines are used for, let's say, creating constants in your program. There's actually 2 ways to do constants. I'll get into both of them here maybe a little bit later today. But basically the processor's job is to strip out the comments and handle these hash mark directives. By the time your program gets through the preprocessor, those preprocessor directives are gone and the comments are completely gone. So what you have now is just basically clean C code, and there's nothing extra in it. Nothing extra in terms of there's nothing in there that doesn't have to do with your program itself. Then it goes into what is really the compiler, and out comes assembly code. Assembly code for the particular processor that you are running your program on. That assembly then goes through the assembler, and out comes object code, which is the compiled machine code, the ones and zeros that your processor understands, but it's not a complete working program. It's just the ones and zeros for the particular functions that you've written. Your object code then goes through the linker, and the linker's job is to construct a complete working executable. So at that point, it brings in the standard C library, and it also brings in any other libraries that you have listed on the command line, and it brings them all together, and then it makes your final working executable out of that. Okay, so what's in these header files? What's in these files that we include at the top of a program? So header files and then a .h, but they are actually just C files. They contain things like constant declarations, type declarations, which we'll get into a little bit later, and function prototypes. So these header files typically do not include any actual code. So they don't contain bodies of functions. They don't contain code that would be executed. They contain just definitions and declarations, but no actual working code. Definitions of things like constants, declarations of types, declarations of functions, but no actual code. I think I showed to you some of these header files last time. We looked at the math.h file, we looked at the standardIO.h file, and we saw that they contained basically just function declarations, function prototypes. So what goes on when we actually compile the program? I typed in clang, tv.c, diag.c, and then -lm to link in the math library at the very end. So what's actually going on? So when you're working with C programs, when you compile a C program, each one of those C files gets compiled separately. Even though I listed them on the same command line, they each get treated separately. So the clang program first goes through tv.c and compiles it, then it goes through diag.c and compiles it, and then finally it links them together. Let me draw you a picture of what that looks like. So we start with tv.c, and then that goes through the preprocessor, and then it goes through the compiler, and finally it goes through the assembler. And then what comes out of that is the object code. Remember, that's just the compiled code. It's the ones and zeros, but it's not a complete working program. And then it turns its attention to the other C file I listed, which was diag.c. That also goes through the preprocessor, and then the compiler, and then the assembler, and then out comes object code. So the important thing about this diagram is that those two files are being compiled independently of each other, and the compiler has no knowledge of the other one. So while it's compiling tv.c, it doesn't know anything about diag.c. And while it's compiling diag.c, it doesn't know anything about tv.c. So it doesn't make any correlation between those files. Once we have the object code from each one of those files, then the linker takes over. It brings in the object codes, the object files from each one of those, and then links in or brings in also the standard library, and it also brings in the math library, and then finally it writes to the disk the executable. Okay? So the big takeaway I want you to get from that is that the two C files, and I already said this, so I'm just going to reiterate it, the two C files are compiled independently of each other. One C file does not have any knowledge about the other C file. And so that's why in each one of the C files, you need to include the function prototypes that that particular file is going to be calling. Okay, so in main, in my tv.c, I call trig.diag. So I need to have a function prototype for trig.diag in it. I don't need the body of it. The compiler knows that the body is going to come later, but having the function prototype is enough to get tv.c compiled. And then in diag.c, I need to include the function prototypes for all of the functions that it calls. So it calls the trig functions, atan, cosine, and square root. And so the math.h file includes the function prototypes for those functions. Okay, but over in tv.c, since this file does not call any of the math functions, I don't actually need to include math.h in it. Right? So my main does not itself directly call any of the math functions, so I actually don't need to include the math.h file in it because I don't need any of those function prototypes. Let me go ahead and save this. I'll recompile it just to show you that there are no warnings. So even though main will indirectly call the math functions, it does not directly call them, and so that therefore the compiler does not need to know how to call those functions when it is compiling tv.c. Okay, does that make sense? Good. I saw one person nod, and so that means that everyone understood. So the last thing I want to do with this particular example is I wrote out the function prototype for trig diag in my tv.c. What is typically done is the function prototypes are put into their own file. So let's go ahead and do that. I'm going to make a file called diag.h, and this will contain the function prototypes of the functions that are in diag.c. So in here, I'm just simply going to put double trig diag, double w, and double pythag diag double w. I'm going to save it, and then in tv.c, all I have to do is include diag.h. And that'll bring in the function prototypes for the functions that tv.c will be calling, which are the ones in diag.c. Okay, right now you probably have a question. Why does standard I.O. have angle brackets around it, and why does diag.h have quotes around it? And that has to do with where the preprocessor goes to look for these files. If it's in the angle brackets, it's going to go look in the directories that are associated with the C compiler itself. So all of the standard C library stuff is searched for when you use the angle brackets. If you use the quote marks, it's just going to look in your current directory. It's not going to go look off in the system directories. So typically, system-supplied header files are included with the angle brackets, and the user-supplied header files are included with the double quotes. That's the easy recipe to remember. There are some subtleties involved with that, but right now, the easy one is to remember if it's a system header file, angle brackets. If it's one that you wrote, double quotes. Okay, let's go ahead and try to compile it. And we see no errors with that. So this is pretty cool. Instead of my C file having to have function prototypes written explicitly in it, all I have to do is put the function prototypes into a header file. And usually what you do is the header file contains the function prototypes of the functions that are defined in the corresponding C file. Okay, are we good with that?
In the clang command, do you continue referring to the C file though for diag?
Yeah, because remember what the preprocessor does when it sees an include is it goes and it reads in that file and then drops it right into my program as though I had written the contents of that file in that C file itself. So what's going to happen here is the preprocessor is going to go and read in the contents of diag.h. It's going to copy it, and then it's going to paste it right in as though I had written those function prototypes right there directly. So that means in my compile command, I don't have to refer to those header files because they're going to be brought in by the preprocessor for me. Does that answer your question?
Yeah, that helps. Thank
Okay.
you.
Another question you might have is, what's the difference between Java's import and C's include? They look kind of the same, right? Different names, but you put them at the top and they refer to like system stuff. So I guess it's kind of difficult to explain, but hopefully you've done enough Java programming that you've seen import sitting at the top. And right now you've done a little bit of C programming and you've seen these include sitting at the top. So as I've mentioned, when you put in include, all the preprocessor does is it goes and it copies out the contents of the file that you're including and then pastes it right into your C code, as though the include had never been there in the first place. Okay, so it's a way for your C file to bring in the contents of another file. I mean, literally, that's what include will do. Anything that you include in your C file, it will literally just go and read the contents of that file and drop it right into your C code. Like, yeah, I mean, to take this to extremes, I could even do like, include the complete works of Shakespeare.txt, and it will take the contents of that file, which I don't have on the computer here, but if I had that file, it would just drop it right into my C code, and now my C program would contain the complete works of Shakespeare in it. I don't know why, but it would. I could even put them entirely inside of comments like this, and then my complete works of Shakespeare is now inside of a comment, right? And then it gets stripped out by the preprocessor. Okay, so the preprocessor is kind of dumb. It doesn't really actually look to see what's inside the file. It just pastes it right into my program. Oh, you didn't see what I was looking at there? Oh, I was literally just putting in like include complete works of Shakespeare.txt, and it would have gone and found that file if I had it on my computer and just pasted it right into my C code. I don't know why I want to put the complete works of Shakespeare in there, but that's what it would do. And then it would go on and try to compile it, and I get a bunch of errors. But the preprocessor does not actually look at the contents of the file; it just drops it right in. So what about imports in Java? So in Java, what import does is it loads in the class file that you refer to. So if you do something like import javax.swing.jframe, then it will go and load in the JFrame class, look at the names of all of the methods that are inside of JFrame, and then it doesn't actually like load the class into your program. All it does is it just preloads the names of all the methods that are in there. And what that allows you to do as a Java programmer is be able to say something like JFrame window, to declare a variable of type JFrame. JFrame window, semicolon. What it's doing is it's bringing all the names of the classes and the methods into the namespace of your program so that you can refer to it by its short name. If I didn't put that import up there, then I would have to say javax.swing.jframe window, semicolon. I would have to give it its complete name. Okay, so an import in Java is not making that class available for your program to use. You can use it anyway without the import. You just have to use the full names. What the import does is allow you to use the short names. I guess it's kind of like, I don't know, what would be another like hypothetical but real world example of that is, I don't know, let's say you're in a classroom, right? And you got all these students in the classroom. And all those students have first names and last names. So initially, what you have to do is you have to refer to those students by their full names. You have to call out their first name and their last name. But maybe at the top of my class roster, I can just say like import Brown. And now everyone who is in my family can be known by their first name, and I don't have to list their last name. So I can just say Barry, and you know who I'm talking about. Or you know that you're talking about Barry. Or you can say, you know, George, and you know you're talking about George Brown. Or you can say Stan, you know you're talking about Stan Brown, right? But if you don't put that import in there, then you have to refer to them by their full names. Does that kind of make sense? Okay, so putting an import at the top of your Java program does not make it run faster. It doesn't make it compile faster. All it does is allows you to use short names instead of long names. You can get by writing Java programs without any imports, and it'll work. You just have to use full names everywhere. So that's the difference. So there's kind of like, after you're doing a semester of Java programming, you might come out of there with this conception that imports are required to make my Java program work, but they're not. You don't have to import anything. In C, you don't have to include anything. You could drop in the contents of those H files yourself. You could put in the function prototypes for the functions you're using yourself, and then you wouldn't have to include anything. Okay, so what I walked you through there was the process of taking some functions in your program, moving them into a separate file, and then creating a header file for that separate file so that the program that is calling those functions just has to include the function prototypes from the header file. That's the whole process. And what I'm trying to do is just unwrap the mystery behind what's the difference between header files and C files and what do I put in them. And I'm walking through to it step by step to say all these are really is just a convenience for you as a programmer so that you don't have to write the function prototypes yourself, and so that you can separate your program into different modules that you can compile separately. Large complex programs are typically broken up into dozens or hundreds or even thousands of separate files, all of which can be compiled independently of each other and then brought together at the very last moment by the linker. I have a friend who works at Google, and he actually works in the Chrome division, so he's part of the people that develop the Chrome browser. And he's told me that if you go and get the source code for the Chrome browser and you compile it from scratch, start it going on your computer, and then go have lunch. And by the time you get back an hour later, it might be done. There are tens of thousands of files that all have to be compiled to get Chrome to work. Each one of those compiled independently of each other, so your compiler is doing a lot of work. It's compiling this one, and then this one, and this one, and there are thousands and thousands of them to do. So let's say you, as the Chrome developer, want to make one tiny change to the browser. Let's say you found a typo in one of the menus, and so you want to fix that menu. You've got one thing to change, one byte to change. Well, if you had to compile it from scratch, it'd be hit compile, or type the command, and then go have your second lunch. That's a terrible waste of time, isn't it? Because all of the files have already been compiled and then just linked at the end, all you have to do at that point is just recompile the one file that changed, and then just link it together, which doesn't take very much time at all. So the initial compile might take an hour, but subsequent compiles might take only a couple of seconds. That's why you want to break up your program into different files, is to save yourself time later on. Now, in this class, we're not going to be writing programs that are so big they take that long to compile, but that's the idea. Break it up into small pieces, compile each one of them independently, and then if you have to change one of them, you only have to recompile that one file and then link them together. Hopefully that made some sense. Okay, I want to switch gears a little bit, and we're going to start.
Can I ask,
Oh, of course.
What handles that? Is that Clang, or is that something else that would handle knowing to only compile, the single file that changed?
Oh, so you have to use a build automation tool that basically runs through each one of these steps and then writes the object code to a file. And then when you say recompile, it quickly scans through your directory and sees which C files have changed since the last time I did a compile. So it looks at the dates and times on each one of the files. And then if it finds a file that is more recent than the executable, then it knows to recompile that one, run it through again to the object code, and then just link in all the objects. So we're going to learn a little bit more about that tool in a few weeks. Any other questions? Okay. So when your program loads into the computer's memory, there's some, I hesitate to call it magic going on behind the scenes, but when you're first learning about it, it seems like magic. One of the things that happens is that the way modern operating systems, and by modern I mean anything since like the mid-90s and forward, so anything in the last 25 years, when your program gets loaded into memory, the operating system, which is the program that runs first on the computer, the operating system's job is to create this illusion for all the programs that they are, each one of them is the only other program running in the computer at a given time. So if you launch Chrome into your computer and then you launch Microsoft Word, the two programs don't have any idea that the other one is running. They could look up and down through all of memory and not see any evidence that there's another program running at the same time. So it's this giant illusion that every program is running and is the only program running on the computer. So the key advantage there is that every program, therefore, can occupy memory in the same way. Every program thinks it's the only program running, and so it loads itself into memory in the same way. And then the operating system's job is to take this illusion and turn it into reality, which is that there are multiple programs running simultaneously. They're actually occupying different slots in memory, but the operating system's job is to essentially like pull this sheet over each program and pretend that it's the only program running. So when a program loads into memory, it has this idea of what the memory of the computer looks like. Now on a 32-bit processor, each program thinks that there's approximately 4 gigabytes of memory. That's how many memory locations you can access with a 32-bit address. So this picture here shows memory. Down here at the bottom is memory address 0, and up here at the top is the highest memory address, which would be 4 billion or so. And remember, every single program running on the computer thinks that this is what memory looks like. This essentially array of memory cells is further divided into 4 pieces called segments. And I'm not drawing them to scale here, but there's these 4 segments. The segment on the bottom is called the text segment. And then the second one is the data segment. And the one at the top is the stack segment. The text segment is further divided into 2 sections. Your program code occupies the bottom half of the text segment. And then things like global constants occupy the top half of that segment. Okay, first of all, I didn't make up the names for these segments. I don't know why that bottom one is called the text segment when it doesn't contain any text at all. It contains the actual executable code for your program plus any constants in your program. So I don't know why it's called text, but it is. That's what it's called. The data segment is itself broken up into 2 sections. The bottom section is where global variables live. and the top half of the segment is called the heap. And then finally, in the stack segment is where local variables are stored. So you've got your program code, global constants, global variables, the section called the heap, and then local variables. That basically makes up all the different parts of your program. And then this segment in the middle is free memory, memory that hasn't been used for anything. And like I said, this is not drawn to scale. The local variables probably only occupies a few kilobytes or a few hundred kilobytes, so not very much. Your program code, at least for the programs that we're running, don't occupy very much memory at all. Maybe, again, maybe a few kilobytes. We don't really have very much in the way of global constants, so if we do, it's probably just a few bytes. Global variables, again, we don't have very many of those. And then we're not using the heap yet. The heap is where we put something called dynamically allocated memory. Any memory that your program needs that is not predetermined, then that goes in a section called the heap. We'll get to that in a couple of weeks. And so really, the data in the text segment is fairly small. No more than 100 or 200 kilobytes. The stack segment is also pretty small, no more than a few dozen kilobytes. And so this free memory really is gigantic. Takes up the majority of the spot, the space, in the memory space. Okay, so why break it up into these different pieces? Well, one thing that the processor does is it marks some of these segments as read-write, and it marks some of them as read-only. Which one of these do you think it would mark as read-only?
The text segment?
Good. There's no reason why your program needs to be writing to the program code. There's no reason why your program needs to be writing to constants. So it marks that segment as read-only so that if your program attempts to change the program code or attempts to change the constants, it will crash immediately. This is probably a good thing, right? Because if your program is trying to modify the code, it means probably some malware is doing something suspicious. So the rest of the segments, the data segment and the stack segment, are marked read-write because they don't actually contain any program code, but they do contain things like variables and things that are changing all the time. So what's the point of this? The point of this is that local variables live in their own section of the memory separate from the other kinds of variables. Okay, local variables come and go. Every time you go into a new scope, which usually happens when you call a function, they go into this area called a stack. Now a stack, if you have studied data structures or at least learned a little bit about data structures, is this data structure that grows and shrinks. So it's called a stack because it's kind of like a stack of trays at a cafeteria. With that stack of trays, you can push things onto the top, you can add trays to the top, and you can take trays away from the top. So it's called a, is it first in, first? No, first in, last out data structure. So the first thing that goes onto the stack is the last thing that comes off the stack. That's the thing at the bottom. What this stack allows us to do is every time we call a function, we essentially put a new tray onto that stack. And that tray, that topmost tray, contains just the local variables for that function. And what that means is that if you're looking down at the top of this stack of trays, you can't see any of the variables for the functions that are below it. You can only see the variables for the function that you're currently working with. And then when that function is done, that tray is removed, and now the variables for the function that you came from are now visible. Okay? So that's the purpose of that stack, is to limit the visibility of which variables you can see. You can only see the variables for the function that you are currently in. That's how the scoping of variables is handled. Every time you enter into a function, a new tray is put on that stack, and every time you leave a function, that tray is removed. And this stacks up, right? So main is sitting here at the bottom of the stack, and then when I call trig diag, that tray goes onto the stack, and then when that one calls cosine, that one goes onto the stack. And the cosine by itself calls some other functions, and so the stack grows a little bit, and then once those functions start returning, the stack shrinks back down.
Do the sizes of these segments change? Like is the memory, is it fixed from the beginning, or do they change dynamically?
Well, when your program gets loaded in, there's another program part of the operating system called the loader, and its job is to set up this memory for your program. And so it takes your program code, and it knows how big that is because it can just look at the size of the file on the disk. So if on the disk it's 5 kilobytes, then it sets aside 5 kilobytes for your program code and loads it in there. It actually just reads in the file and just copies the bytes right into memory. Then it also looks in your program for any global constants, and it allocates space for that. It looks in your program for any global variables, and it allocates space for that. And then at that point, the loader's done. Right? You've now got your program loaded into memory. Okay, so for a particular program, this size of the memory map will remain a constant. Right? You're not going to be adding any more constants because the compiler already knows about all the constants. It's looked through your code, and it knows about all of them. It knows about all the global variables, so that's not going to change. So that part of the memory is then fixed. Now, the segments might be different sizes for different programs. Like Chrome is a huge program, so its chunk of memory will be large. Your programs that you're writing currently are really small, so they might fit into a small little space. The part that does grow once your program is running is this heap. That's going to start growing upward as your program allocates memory. And again, we're not going to get into that just yet. But something you do know about is if you've done Java programming, you know that there is this word called new that creates objects. And so when you call new, it's actually allocating space on this heap. So every time you create an object in Java, the heap grows by a little bit. And every time that object is reclaimed by the garbage collector, the heap then shrinks a little bit. So the heap grows and shrinks. And then the stack also is growing. However, the stack starts at the top and grows downward. So the heap grows upward towards higher memory, and the stack grows downward towards lower memory. Now, if your program allocates a bunch of memory and it has a whole bunch of function calls, those two could actually collide with each other. Not very common because you got a huge gap to fill. But if you do get a what's called a stack collision or a heap collision, it means your heap grew up and met the stack, or it meant your stack grew down and met the heap. And then your program at that point crashes because now these two segments cross each other. Does that answer your question?
It does. Thank you.
So there's this great visualization tool I called the, it's actually the Python tutor, but it also works with C and some other languages. And you can type in a snippet of a C program, and then you can step by step go through the program and actually watch the data being built in your program. So I'm going to go ahead and type in a really short program. Here, let's make a function called square. And it takes in a parameter called x. And all this square function does is it takes x and multiplies it by itself and then returns that value. And then let's write a main, which is going to make a variable called a, whose value is 5. And then it's just going to call square. But we'll do a plus 2. Okay, so the program is going to create a variable called a, assign the value 5 to it. Then it's going to call square with a plus 2, and then that's going to go into the variable called s. And then finally we could print out the value of s. So I'm going to click on Visualize, and it's going to compile the program and then bring us up to a screen where we can watch this program running. Okay, the red line here indicates what line the program is going to execute. It hasn't executed it yet, but this is the one it's going to do next. And then later on, in a moment, we're going to see a green arrow, and that's going to indicate the line that just executed. So let's click on Next. Oh, by the way, here's our stack on the right-hand side. We can see that the stack now contains just the variables for main, which are A and S. So remember, the stack is kind of like that tray of, or stack of trays at a cafeteria, and all we can see is the topmost tray. Now the stack in computers grows downward, so you're going to see the stack growing downward, but just be aware that the top of the stack is down here at the bottom. Okay? So right now the only thing on the stack is main, and we got two variables A and S. And so it knows about these variables A and S because the compiler has gone through the program and learned the names of all of the variables and what scope they're in. So it knows that A and S are inside of main, and we have question marks here because we haven't assigned their values yet. They contain just garbage, junky values at this point. I'm going to click on Next. And now we're about to execute the line that assigns 5 to A. So we can see that over here, A has taken on the value of 5. S still doesn't have a value yet because we haven't assigned to it. So now we're going to execute line 10. So whenever you do an assignment in whether it's Java or C, an assignment always has what's called the left-hand side and the right-hand side. The left-hand side is the stuff that goes on the left of the equal sign, and the right-hand side is the stuff that's on the right-hand side of the equal sign. Those are actual, like, compiler computer science terms, LHS and RHS. I'm not making those up. So this is the left-hand side, and this is the right-hand side. When you're doing an assignment, the right-hand side gets done first, and then the left-hand side gets done. So it's going to call square, and then it will assign it to S. Okay? So that's really important to know that when you're doing an assignment, it kind of goes backwards. It does the right-hand side first, and then it does the left-hand side. Okay, so we're going to click on Next, and now the arrow pops up to here, because now we're inside of square, and you can see a new tray has been pushed onto the stack, and now, because this one is highlighted, these are the only variables that we can see. We can only see X and SQ. Click on Next. You can see that now X has the value of 7. Where'd that 7 come from? It's a question for you. Where'd that 7 come from?
It came from the value that we passed into square.
Yeah. So when we called square, the computer took the value of A, which was 5. It added 2 to that to give you 7. And then that's the number that gets passed in to square and appears as the variable X. The important thing to get out of that is that square has no idea that X was the sum of 5 and 2. All it knows is that the value of X is 7. It doesn't have access to the original 5 and 2 that made up 7. Okay? That's a really important thing to know, is that when you call a function, the values of the parameters are evaluated, and whatever the result of that expression is, that's what gets passed in as the parameter. Okay, it's not the expression itself. So a plus 2 does not go in as x. It's the value of a plus 2 that goes in as x. Okay? So we're inside a square. X has the value 7. We're going to click on next. You can see the value of SQ is 49, which, you know, what you got from multiplying 7 by itself. And now we're going to return SQ. So the value of SQ, which is 49, is going to go back up into main. And what happens to that? So we've just evaluated the right-hand side. And now that value of 49, which is the value returned by square, is going to get assigned to S. Let's click on next again. And we can see in a moment here that tray is going to be removed from the stack. And now 49 has gone into S. And what happened to the tray that represented square? Where did it go?
It's gone. It's been popped off the stack.
Yeah, it's gone. And all the variables that are associated with it also went away. So what that means now, of course, is that main doesn't have access to those variables. It can't get access to X and SQ. So each function can only see the variables that are contained within it. Okay, and then last I'll click on next, and we'll see the value of 49 got printed out up here. Okay. So let me do another example. So I've got a function here called max, and its job is just to figure out which of the two parameters that are passed in, which one is the greater one. So in this function, I've got a variable called m, and m is just going to be which of a and b is the greater one. So if a is greater than b, then m will take on the value of a. If b is the greater one, then m will take on the value of b, and then I just return m. And you may be wondering, like, why don't I just say if a is greater than b, return a? The reason for that is so that by creating separate variables, we can see in the visualizer those values being calculated, rather than just sort of mysteriously popping back into the previous stack frame. So let's go int x equals, let's say 5, int y equals 12, int z equals 10, and then we'll go int result equals max of x and y minus z. Let's start this up. So initially, we've got, by the way, I use the term tray and cafeteria stack, but really the technical term for this is a stack frame. This is called a frame here. And so inside the frame are the variables that are local to that particular function. So I'll click through the first three statements, and it's going to assign the values 5, 12, and 10 to x, y, and z in turn. And now, when I click on next, what's going to happen? So tell me, you know, what visually will we see on the screen when I click on next?
You should see a new stack frame for max.
Mm-hmm.
And it will have, yeah, it'll have the variables. Yeah.
Okay, so right now we've got the stack frame for max. We've got the three variables, a, b, and m. None of them have values yet because nothing's been assigned, but I'm going to click on next, and now it's going to go into the body of the function. When I click on next, the values of a and b will get filled in because now the parameters have been passed in. So as a prediction, what's going to be the value of a and what's going to be the value of b?
A should be 5 and B should be 2.
Good. So A should be 5, and B will be the result of y minus z. Y is 12 and z is 10, so 2 should go in as B. There they are. Perfect. So once again, the max function has no idea where those 5 and 2's came from. It doesn't know that 5 came from x, and it doesn't know that 2 came from 12 minus 10. It also doesn't even know what variables those were associated with. All it gets is the values. And you may have heard that term, call by value. So the values of those variables are evaluated before the function is called, and then the values of those expressions are then passed in as the parameters to that function. The function itself has no idea where those values came from. Okay, so we're about to execute statement number 4. After I execute 4, will this arrow jump to 5 or will it jump to 7? What do you think?
I think it should jump to 5.
Okay, so the prediction is go to 5. Let's try. You're correct. It went to 5. And so we can see that now the value of m is 5. And then when I click on next, what are we going to see visually once I go to the next line?
The stack frame for max should disappear.
And what else will change?
And the return value should be put into the res variable.
Good. So I'm going to click on next. We should see the stack frame for max disappear, and we should see the value of res appear. And there it is. So I just want to point out, and this may seem obvious to some of you and not obvious to others, that when the code is generated for max, both of these assignment statements appear in the code, both the one that assigns A to M and the one that assigns B to M. So both of them are there. What happens is this condition is evaluated, and if the condition is true, then it tells the processor to go to the instruction, go to the memory address for that instruction that does the assignment of A to M. And if that statement was false, it tells the processor to jump over the statement for assigning A to M and instead do the one for assigning B to M. And the reason why I say that is because some studies have been done and shows that some students come out of an introductory programming course with this conceptual model of how they think the computer is actually working. And some people think that the program somehow magically knows whether that statement is going to be true or false, and then inserts the correct instruction depending upon whether it's true or false. So basically, the program kind of rewrites itself depending upon whether that was true or false. And that is not the case at all. Both those statements are there. It just tells the processor, do this one or do this one. Okay? Later on, probably as early as next week, we'll actually look at the assembly code, and I'll kind of show you how to read the assembly code, and you'll see that both of them are in there. And there's actually these instructions that say, if this is true, go execute this instruction. If it's false, jump over that one and go do this other one instead. Okay, let's do one more. So this one is a function called diff, and its purpose is to tell you the difference between A and B, but it's going to give you a positive difference. So if I pass it 3 and 5, it should say 2, and if I pass it 5 and 3, it should also say 2, because the difference between those two is, between A and B is 2. So the first thing it's going to do is subtract the two numbers to get the real difference, and then we're going to pass it into a function called absolute value, which is going to just give us the positive difference between them. So let's call this dd. Okay, so there's a function there called absolute value, but we need to write that. And we're going to do this absolute value the way you were probably taught how to do absolute value in grade school, which was if the value is negative, convert it to a positive. If the value is positive, just leave it alone. So if x is less than 0, which means x is negative, then go ahead to assign to a the value of negative x. Okay? So if x is negative 5, we're going to assign to a the value of negative 5, which is positive 5. If x is positive or 0, then just simply put into a the value of x. And then finally, a main. We'll go int, I'm running out of variable names. Let's call this, let's go ahead, call x equals 3, int y equals 5, and then we're going to call diff with the value of x and y, and then that'll be it. We don't have to print it out really because our visualizer lets us see the values. Server's overloaded. Let's try it again. I'm not the only person that uses this particular tool. There's probably other courses all around the world that are also using this tool at the same time. And so sometimes their server gets overloaded. I understand that actually this particular tool, the visualizer, is basically a desktop computer running underneath someone's desk in a university somewhere. So it's not the most powerful machine in the world. It's running as a free service by this particular professor. And the only time that he knows that something is wrong is when someone emails him and says that you need to reboot that system. And in fact, I went and looked at his page and he says, for the most part, I'm so busy, I pretty much ignore emails. So if you send me an email, I might get to it in a couple days. So there was one time when the system was overloaded. I was just about to go do my class, and it kept giving that error message that says the system was overloaded. And so I looked up the professor's name, and he happened to work at a university that I knew some people at. So I sent that person an email and said, hey, could you go knock on that little professor's door and tell him the system was overloaded? And then he gladly went and did that, and then the system worked fine. So I was happy that I knew someone who happened to work at that university. Anyway, so here we are inside of main. We're going to click on next. And we'll see that 3 and 5 go into x and y. And now we're going to call diff. So we're going to get a new stack frame down below main with our A, B, D, and DD. If I click on next, we'll see that A and B get filled in with 3 and 5 as we expect. And now D is going to get filled in with what value?
D will be the result of the subtraction, which should be -2.
Good. So there's -2. And now I'm going to click on next, and what will we see on the screen?
We'll see a new stack frame for absolute value with the variable set up but not populated.
Good. So we've got a new stack frame. So here's now a third stack frame. So we've got a third tray sitting on top of this cafeteria stack. The value of -2 comes in as the value of x. And then we're going to do one of these two things. So if x is less than 0, which it is, it's -2, we're going to see it execute statement number 12. So that means A is going to be the value of -x, which is hopefully 2. And then it jumps over the else portion of the if-else, and it goes to the return. So 2 is the value of A. That's the value that's going to be returned up to diff. So what will we see change in this right-hand side of the screen?
The stack frame for absolute value will disappear, and then the value from its A2 should go into DD.
Yep.
Yeah.
And then that one's going to return, and the value of 2 is going to go up and appear as D. And then the program is done. So what I wanted to show there is that if you have a function that itself calls another function, then you're going to get this piled up stack frames. And I don't know if you noticed, let me go back to the first over here. Inside of this stack frame, we have the variables x, y, and d. Inside of, let me jump forward here. Inside of this stack frame, we have a, b, and d. And this d inside of diff is different from the d inside of main. So they have the same names, but they are different variables because they occupy different stack frames. And then if I jump forward a little bit further, we have inside of absolute value x. And this x is different from the one inside of main. And this a is different from the one inside of diff because they occupy different stack frames. This is how you can have programs that have the same variable names in different functions, and they don't collide with each other. This is a powerful thing for programmers because it allows you to essentially isolate each function from other functions. Once you create a new function, you can create variables inside that function and not have to worry that those names are going to interfere with the names of variables in other parts of your program. And to take that a step further, it means that maybe I, working in a team of programmers, could hand off the writing of that function to someone else, and they don't have to worry about the names of variables. The only time they would have to be worried about something is the name of the function itself. That can't be the same as any other function. And C is not an object-oriented language, so I can't bury it inside of a package. I can't bury the name of that function inside of a package and then therefore have the same name. But I also have to worry about, as a C programmer, I have to worry about things like global variables and global constants. Those have to be shared amongst all the functions as well. So global stuff, function names are global, global constants, global variables have to be unique, but within a function, I can reuse the names of variables as I see fit. Okay. So I hope you got a little bit out of that demonstration relating to this picture that I showed you. That as my program is running, this stack is building up, or building down as it were, containing each one of the stack frames that themselves contain just the variables for that function. And so as the functions call each other, the stack grows, and as those functions return, the stack shrinks. And so as a program is running, especially a long-running program, that stack may grow and shrink and grow and shrink and grow and shrink thousands of times per second. Sitting up at the very first entry on the stack would be something like main, and then below that would be all the functions that main itself is calling. There's a chat question that says, there aren't things like namespaces. How do you avoid naming conflicts with functions that you're not aware of, like functions that are in the C standard library? That's a problem. It means that if there's a pre-existing function called printf, and you define one called printf, then there's a collision there. And the compiler will throw an error message and say, hey, you've got two functions here called printf. That's an error. You can't do that. And so one way to get around that is, first of all, you have to kind of like know the names of the common functions that are in the standard library and then avoid those. But also, if I don't link in the math library to my program, I can create a function called cosine, for example, that overlaps with the math library one because I'm not going to link that one in. And so there's no collision in that case. Does that make sense? Right, so that's why a lot of these functions are broken out into their own libraries, so I can selectively bring in the ones that I just need and not have to worry about the ones that I'm not bringing in. The ones I'm not bringing in, I can use those function names and there's not going to be a problem. As soon as I bring that library in and link it in, then I got a problem. Now, if you use a language that supports the concept of overloading, in which you can create a second function with the same name, as long as it accepts different parameters, then the compiler can keep them straight. But C is not one of those languages. C does not support the concept of function overloading, and so you can't have two functions with the same name that accept different parameters. It just gives you an error. That has actually been proposed as an extension to C, or hopefully part of the C language with the next version of C coming out, which I think is C20. Right now we're using C11, which was the standard proposed in 2011. C has not grown very much as a language. It's pretty much stayed stable, and that's by design. They don't, since C is kind of foundational to a lot of the other programming languages and operating systems and embedded systems that are in use in the world today, the people who work on C don't want the language to change a whole lot. So they've kept it pretty stable. So the last major version of C was C11 in 2011. This next version that's coming out is C20. So you see there's a 9-year gap between versions of the C language. And in that version, there's a proposal to make it so that C supports the idea of function overloading. As long as you have a function that accepts different parameters, so it has to accept different types or in a different order, then you can have a function with the same name. So that could help a little bit. Function overloading is like one of those things that programmers have been clamoring for decades. Like, other languages do it, why can't C do it? What will it hurt? It won't really hurt much. So that's coming up, and I'm kind of looking forward to that a little bit, because it means that I don't have to worry so much about other functions that are out there. And that may also answer the question, like, why isn't there just one include for everything? Why can't I just like include star.h and get all of the C standard library and all of math and all the networking code and everything I might ever need? Well, now you've got a whole bunch of functions potentially in your namespace that means you can't use those function names. And that could be a real problem. So you really want to keep the includes in your program down to just the bare minimum. Which are the ones that I need, and I'm going to not do the other ones, so that I don't pollute my namespace with a bunch of functions that I don't need. Okay, it's almost 11 o'clock. We're going to take a short break, let you go get some coffee or something to drink or go to the bathroom. And then when we come back, we're going to talk about the programming assignments for this week. So I'm going to pause the Zoom recording. The YouTube recording I can't pause. So you'll hear some intermission music.
Recording stopped.
Oh, let's see. There were some other questions that I missed in the YouTube chat. Is it possible to have, by mistake, circular includes? Yes, absolutely. Your program could include file A, and then file A could include the one that you just came from, and so you can create this circular include. Now, I think a lot of the modern preprocessors will detect that if that happens, and will throw an error to say that you've got includes that are going in a circle. Some older preprocessors didn't catch that, and you could actually just lock the thing up, right? Because now A is trying to include B, and B is trying to include A, and it just gets stuck in this cycle. It goes around and around. So there's a little trick that some programmers, many programmers do, which is in file A, you could define basically a flag that says, hey, file A has been included already. And then file B will check to see, and then what file A will do is it'll check to see if that flag is already set. If that flag is already set, then it knows that A has already been included and it won't include it again. So it kind of like cuts that cycle off as soon as it detects it as a loop. Oh, I see. Someone's already mentioned about things called header guards, and that's exactly what that is. It's just a little check to see if that file has already been included. And if it is, don't include it again. Not something I need to get to in this course. But as an experienced programmer, probably something you should get used to, is the idea of these guards to make sure you don't include a file more than once. And even if you don't have cycles in your includes, it still can be a problem. Like let's say you have your main program, and that includes a.h, and a.h includes math.h. Okay, and then your main program also includes b.h, and b.h also includes math.h. Right, so now you got math.h basically being included twice, and then that creates a problem because the compiler says, hey, you're doing function declarations more than once. And so that's what also those include guards are there for, is to make sure that things like math.h don't get included more than once. Got a question. You got a problem with the flag assignment? Why don't we, when we come out of the break, why don't we go ahead and do that? What are the default naming conventions in C? I feel like there isn't really one standard as there is with Java with camel case and C# with Pascal case. Well, I guess there's two kind of standards. There is the older standard, which stated that for the most part everything should be in lowercase. And if you have multiple words in your variable names, like the last name, instead of doing like in Java, which is last and then name stuck right to it with a capital N, you instead separate those names with an underscore. So it'd be last underscore name. But with the popularity of languages like C and Java, which, not C and Java, C++ and Java, especially Java, which encourage the use of camel case, where you have the capital letters interspersed in the variable names, then you're seeing more C code written like that. So it depends kind of on the age of the programmer and the age of the code base you're working with. If it's an older code base, you're probably going to see the older naming convention with the underscores, and if it's a newer code base, you're probably going to see the camel case. The compiler doesn't care. Good morning, Happy Will. How are you doing? What part of the world are you from? Another comment is, when I was in college, I was learning C++. The professor just said, here are all the different styles out there. Pick one and stick with it. That's ultimately what you need to do. Is when you go into an employer who has some existing people working on projects, you just have to use whatever conventions they're using. Hopefully, they've written out a document that gives you their particular style of writing code. Where the braces go, how to structure things like switches, how to do naming conventions for variable names, constants, type declarations. Hopefully that's all been spelled out so that you can follow along and stick with the same naming conventions they've got. You're from Portugal. Some people are from Portugal. So you must be about, I'm guessing, maybe 8 hours ahead of us. So it's probably close to 7 at night-ish. Why don't we stop the music here at this point?
Recording in progress.
Okay, let's take a look at the programs that we're going to be writing for this week. So there's 3 to do. There's 2 warm-ups and 1 actual level up assignment. The first warm-up is called Sigmoid, and there's some background material here about artificial neural networks. The idea there is this is an artificial intelligence technique that's used to train a computer to make decisions kind of the way the human brain does. The human brain takes in a whole bunch of inputs coming from our senses, and then they run through the neurons that are in our brain, and those neurons make a decision. They're working together, they make a decision. And so each neuron has a nucleus, and then an axon terminals that themselves connect to other neurons. And so they form this neural network. Well, inside of the cell is basically a little computer. And the computer is really simple. All it does is it takes the value of the input, the values of the inputs that are coming into the neuron, and it basically performs a little calculation on them. It might look at, let's say, the majority of them. If the majority of the inputs are triggering, then the output of the neuron will itself be like basically a 1, right? So if the majority of the inputs are a 1, then the output is a 1. Or if maybe it's not necessarily just a simple majority. Maybe it's something like if these 5 inputs are on and then these other 2 are on, regardless of the state of the others, then the output is a 1. So there might be some kind of function associated with all these inputs coming in. And so from a programmer's point of view, if you want to simulate one of these neural networks, you do have to kind of figure out what's a mathematical function I can use to determine whether or not the neuron fires a signal down to the next neuron or not. And so one of the formulas you can use is called the sigmoid function. And here it is. It's 1 over 1 plus e to the negative x, where x is just the input value. And visually, this is what it looks like. It's this nice curving line. And so all you're going to do is you're going to write a function to calculate the sigmoid function. You should have 2 functions in your program, one called sigmoid that takes in a float, value of x, and returns a float. And all it does is it just computes this value. It doesn't print anything out, doesn't get any input from the user. It just simply calculates that function. And then your main should generate a table. So the table should go from -5 to +5, and the second column should be the output of that function. So this is what the output of your table is going to look like when you're running your program. So loop from -5 to 5 in increments of 1, plug it into the sigmoid function, and just print out the 2 values. That's all. Doesn't have to be anything more complicated than that. The purpose of this assignment, this program, is just simply to get you used to the idea of writing a function, calling it in your program, and being able to write a compile command that puts together all the pieces of your program, which is the one file containing the 2 functions and the math library. So with the math functions, the one you need to know about is called exp for computing the exponent raised, what is it? The Euler exponent, right? E raised to some power. So that's all it is. Just write a really short program, no more than about 20 lines or so, and then just make sure it compiles, runs, and then upload it to our class website. Okay, whoops, that's the first program. The second program is called the Collatz conjecture, and this was proposed in 1937, and it works like this. Start with any positive number, n. If n is even, then divide it by 2, and if n is odd, multiply by 3 and add 1. And then just repeat that. And the conjecture is that the value of this number is going to fluctuate up and down, up and down, up and down, and eventually it's going to go to 1. So if I start with 6, 6 is even, so I'll divide it by 2 and get 3. And that's odd, so I'll multiply it by 3 and get 1 and get 10. And that's even, so I'll divide it by 2 and get 5. That's odd, so I'll multiply it by 3 and add 1. And that's even, so I divide by 2. That's even, so I divide by 2. That's even, so I divide by 2. That's even, so I divide by 2, and I get 1. Now, if I was just to continue this, 1 is odd, so I'd multiply by 3 and get 2. I multiply by 3, add 1, and get 4. That's even, so I'd get 2, and then 1. And then I get into this cycle where it goes 1, 4, 2, 1, 1, 4, 2, 1, 1, 4, 2, 1. So we can say that really the cycle ends when we get to 1, because as soon as you hit 1, then you're going to go 421, 421, 421. So the conjecture is, and it's called a conjecture because no one has ever proven this to be true, is that no matter what number you start with, you'll always end at 1 eventually. No one's ever proven that to be true, and no one's ever proven that to be false. That's why it's still called a conjecture. So your program should prompt the user to type in a starting number. The starting number needs to be greater than 0, so check to make sure it's not negative. If it is invalid, if it is negative, then re-prompt the user to type in a number again. So keep looping your program until they type in a correct number. Then print out the Collatz sequence. You can just print it out all in one line. If it's more than one line's worth, the terminal will wrap the lines around for you, so you don't have to worry about that. Again, this is a warm-up program. All we're doing is just exercising the idea of using functions and printing things out. And then also print out the length of the sequence, so how many numbers are in the sequence. For this one up here, the length is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That includes the starting number. So your program should have 3 functions. One called getStart that prompts the user. One called nextCollatz, and the job of nextCollatz is simply to calculate the value of the next value. Don't print anything out. Just simply calculate the next number in the sequence. And then main calls nextStart to get the starting number, and then calls nextCollatz in a loop to actually print out the sequence. And then it stops when you get to 1. There's one additional hint here. The values in the sequence can get large, and they can exceed the size of an int, so you may want to use long, which is 64 bits, and will give you a much greater range of numbers you can deal with. As before, upload your C program, and then you're done with this one. And then there's one more to do. Oh, whoops. We got more here, optional extensions. So doing this extension will not change your score on the program, whether it's complete or incomplete. It's just something kind of fun for you to do if you want more of a challenge. And that is find the starting number between 1 and 1,000 that results in the longest sequence. So what number between 1 and 1,000 gives you the longest Collatz sequence? So if you're going to do this, this should be an add-on to your program. You should still have the original program, which prompts the user for a starting number and displays the sequence, but then it could go on and do this extra step to find out which one results in the longest sequence. Okay, and then one more program. This one is called Making Change. So the example I've given you here is you've bought something at the store for $23. You hand the cashier $40, and so you'll receive $17 in change. If the cashier is doing his or her job, you'll get back a $10 bill, a $5 bill, and 2 $1 bills for a total of 4 bills. You'll get 4 sheets of money back. So you're going to write a program that prompts the user to type in the amount of money that you'll be receiving back, and it tells you how many bills you'll get back. All right, it's a little strange here. It doesn't tell you which bills. It just tells you how many you'll get back. So if the change amount is 17, you'll get 4 bills back. That's all your program's going to do. It's just tell you how many bills. So we'll assume, for simplicity, that the denominations are 100, 20, 10, 5, and 1. If the user types in a negative amount, loop back and re-prompt until they type in a positive number. So here's how it might work. So let's say you start with $164 you're giving back in change. First, calculate how many $100 bills you'll need. That's 1. So you'll subtract 100 from 164, leaving 64 remaining. Then calculate how many $20 bills you'll need. You'll need 3. So subtract $60 from 64, leaving $4. Calculate the number of $10 bills you'll need, which is none. So subtract 0 from 4. How many $5 bills will you need? Also none. So subtract 0 from 4. And then finally, calculate how many $1 bills are needed to give you the remaining amount, and that's 4. So you'll sum that up. 1 plus 3 plus 0 plus 4. Whoops, that should be 1 plus 3 plus 0 plus 0 plus 4 equals 8. And this is the number your program displays. So this is not the only way to do this calculation, but this more or less mimics the way a human would do it. If you're standing at a store, the human is probably starting with the largest bills and then working their way towards the $1 bills. So your program should have, at minimum, 3 functions, one called bills that does this calculation, one called get amount that prompts the user for an amount and makes sure that it's positive, and then one called main that calls the other functions. There's a couple of optional extensions for this. One of them is, well, you could prompt the user to type in different bill denominations. So let's say, for some reason, your particular country uses $86 bills, $29 bills, $17 bills, $4 bills, and $1 bills. And maybe people who live elsewhere have $99 bills, $49 bills, $19 bills, $9 bills, and $1 bills. So write a new version of the program that lets the user type in the values for these 5 denominations and then uses that to do the calculations. Program works otherwise the same as before. Subtracts off the larger ones, then subtracts off the next larger ones and calculates the total number needed. And then optional extension number 2. Now this one's probably going to take some research on your part. So this one is definitely a challenge. For our particular, in the United States, our particular system of currency, using 100, 20, 10, and 5, and 1, when you start with the largest bill and work towards the smallest bill, you will always end up with the optimal number of bills, the fewest number that you need. But if you had denominations like 51, 28, 4, 3, and 1, if you work from largest to from largest to least, you'll actually end up giving out more bills than you need. So for example, if the change amount was $6, our algorithm would give out 4, 1, and 1. We dispense the 4s, leaving 2, and then we dispense 2 1s, and then that's the whole amount. But actually, the optimum one would be 2 3s. That's only 2 bills instead of 3. So for this particular system of currency, just starting from the largest and working your way towards the least does not necessarily give you the optimum answer. So what your programming is going to do is calculate what's the optimum number of bills. And this is where the challenge comes in, because you'll probably have to do some research to find out how to do this. One possible strategy you could use is write a program that calculates every possible combination of bills that add up to the desired amount, and then just find the one that uses the fewest. So this is a brute force way of solving it. You basically find all the different ways to give out the change and then figure out which one is the most optimal. The other way to solve the problem uses recursion. It's a problem-solving strategy called dynamic programming. That's where you could plug those into Google and find out how to do a program like this. What it does is it doesn't do a brute force, but it basically comes up with different branches of ways that it could calculate the change, and then it kind of follows the best branches that it has so far in order to figure out what the remaining branches are. Okay, so those are the 3 programs that you're writing this week. I guess I want to, at this point, remind you that because there are only suggested due dates and no real solid due dates, it's very easy in this class to fall behind. To think, well, programs aren't due this week, so I'll put them off until the weekend, or I'll put them off till next week. And if you have more pressing deadlines, like you've got a test coming up in another course, or you've got a large lab assignment in your physics course, then please go and focus on that and do that. But don't do it at the complete expense of this course, because you're going to find yourself falling so far behind that there's a lot of catch up to do towards the end. And then you're not going to get a whole lot out of the course. So even if you do end up putting off the assignment for a day or two, make sure you do get around to it and doing it. This weekend, I am going to post the first of our what are called reflection surveys, which is a chance for you to kind of write down what have you learned so far and what still seems unclear to you, and kind of just reflect back on the previous 2 weeks and tell me and tell yourself, what have you gotten out of the course so far? There's going to be those reflection surveys every 1 to 2 weeks or so, and those are there to kind of keep you as a reminder that the course, the pace of the course is still moving forward, and you need to kind of keep caught up on things. And it's going to become part of that overall portfolio of work that you've done at the end. We're going to look to see, did you turn in those surveys at the end of the semester? So are there any questions at this point? Okay, so what I want to do for the remainder of time we have, which is about half an hour or so, I want to show you a program that's going to help you out with that Collatz conjecture program. I'm not going to write that program for you, but I'm going to write one that's similar. And so I'm going to talk about random number generators. Now, computers have a built-in function for generating random numbers, usually called rand or random. And it'll give you a number that appears to be random. But since it's running on a computer, it's actually just following an algorithm. And the algorithm just tells it step by step how to calculate a random number, which means it's not really random. It just appears to be random because it has done a calculation that's complex enough that to us humans appears to be random, but really it's quite deterministic. The first random number generators were proposed way back in the 1940s. In fact, the one I'm showing you on the screen here is called the von Neumann random number generator because it was developed by von Neumann, whose name probably has popped up in your computer architecture course. But back then, in the 1940s, computers were slow, they were expensive, they didn't have very much memory, and so the random number generators of that time were fairly simple. But the cool thing about them is, to this day, up here in 2022, although we don't use exactly the same algorithm anymore, we still have the same basic concept of how they work. And that basic concept is this. You've got this box, I'll call it, which contains your random number generator algorithm. And the input to that box is called the seed. It's a number to start things off. So the seed goes into the random number generator algorithm. The RNG does a calculation on the seed, and then out pops a random number. And it's actually called a pseudo-random number because it's not really random, but it appears to be random. And then that number that came out of the random number generator is then cycled back in as the seed to the next iteration. The initial seed is used to kick off this calculation, and then the subsequent numbers that are produced are used as the seed for the next iteration. So every random number that gets generated was itself generated from the previous random number. Here's how the von Neumann random number generator works. You start with a 4-digit number, you square that 4-digit number, and when you square a 4-digit number, when you multiply a 4-digit number by another 4-digit number, you'll get a number that's about 8 digits long. So it doubles in length. You're going to extract the middle 4 digits, and that'll be your random number. So this squaring and extract the middle 4 is the algorithm that's going on inside that box. And then that number that comes out is going to be used as the seed for the next iteration. So that's this green arrow going back around. Let's do an example. Give me a 4-digit number. Just off the top of your head.
Like 1,526.
1,526. Okay. So we're going to square that number. And I just did it on the calculator on my computer, and I get 2,328,676. And now I want the middle 4 digits. Now when I multiplied this 4-digit number by itself, I actually ended up with a 7-digit number. But usually I should end up with an 8. So I'm going to pretend this is an 8-digit number by putting a 0 in the front. Now I've got 8 digits. So the middle 4 digits are these right here, 3286. All right, so let's take 3286 and we're going to square it. And I get 10,797,796. And again, I'll take the middle 4. 779, no, not that. 7977. And that becomes my next random number. So you can see how each number is being used to generate the next number. Okay, so the question then becomes, how do I actually write this in C code? So we're going to write this program. Now, I'm not going to include the library for doing the built-in random number generator. We're going to be using our own. So let me let's write the function that actually does this calculation. So it's called int VNRNG, the von Neumann random number generator. It takes in a seed, and then it produces an integer as a result. So the first thing we're going to do is take that seed and multiply it by itself. And now we need to extract the middle 4 digits. So how do we do that? Now you might be inclined to think, well, why don't we convert this into a string, and then we can just use the string manipulation to peel off the numbers we don't need. But we can actually do this entirely with numbers. So let me see if I can walk you through how to do this. Let's say I gave you the number 537. And I said, what would happen if I took the number 537 and I divided it by 10?
It would be 53.7.
Good. But if we're a computer, we're doing this as integers. 537 is an integer, and 10 is an integer. So when you divide by 10, we don't actually get 53.7. We get
53.
53. So if I divide an integer by 10, I essentially peel off the least significant digit. It goes away. So if I took an 8-digit number, what could I divide it by to get rid of the 2 least significant digits, which I don't want?
100.
Yeah. So if I took a number like 1, 2, 3, 4, 5, and I divide it by 100, that gives me 1, 2, 3, and the 45 went away. So if I take the number and I divide it by 100, that'll get rid of 2 of the digits that I don't want. Now I need to get rid of the other 2 digits, the ones on the other side. So going back to my 537 example, what if I did 537 modulo 10? what do I get? So I divide by 10, and this gives me the remainder.
You'll get 7.
I'll get 7. What happened to the 53?
It's modulus, so it's like that's like not in the in like the set of acceptable values.
Right.
So it got cut off.
Right. So I started with 537. I divided it by 10, and I kept the remainder. So the 7, which is the remainder of dividing by 10, is kept, and the 53 goes away. So the modulo 10 essentially allows me to isolate that least significant digit, to pull it out. So what could I do to 537 if I wanted to keep the 37?
Modulus 100.
Good. Modulus 100 is 37. And now the 5 goes away, and I keep the 37. So if I take my 8-digit number, this one here, 10,797,796, I can do divide by 100 to get rid of the 96. And then how do I get rid of the 10?
Modulus 100.
No. If I do modulus 100, that'll keep the 77.
10,000?
Yeah, modulus 10,000. And that'll keep the last 4 digits, and it will throw away the other ones. So I'm going to divide by 100 and then modulus 10,000. And that'll give me the 4 in the middle. It'll even work for the 7-digit number. I'm going to divide by 100 to get rid of 76. And then I'm going to modulus 10,000 to keep these 4 digits and throw away these 2. Doing this all with integers, so I'm never going to get a decimal amount. Okay, so now I just need a main to call that repeatedly, and let's just see all these numbers that come out. Let's do 100 of them. So I'll start my seed. Let's go int s equals 1526. And I'll go int r is equal to von Neumann random number generator of s. So I'm going to take my seed number, 1526. I'm going to plug it into the random number generator. Out's going to come a random number, which I'm going to call r. Let's print that out. And then the last thing I'm going to do is I'm going to take r and put it back into s, so it becomes the seed for my next iteration. Let's save that. And compile it. So there was a suggestion on YouTube, in the YouTube chat, basically what I said before. Can I convert it to a string and then use the substring functions to pull out the middle 4? And sure, we could, but here's a way to do it entirely with arithmetic. Okay, so we get 3286, which was the next number we calculated, then 7977, then 6325, and then 56, and then 31, and then 9, and then 0. And then at that point, the random number generator falls apart. Let's try a different starting number. Let's try doing, someone suggested 4523. So this one produced a different sequence. We started with 4523. The first number that came out was 4575, then 9306, then 6016. So this produces a nice long sequence. You can see it keeps going until at some point it also falls apart, and then we get stuck in this cycle where we're going 4100, 8100, 6100, 2100, and then 4100 again, 8100, 6100, and it gets stuck. So this random number generator is not great. It produces a sequence that might be short, it might be longish. Usually they eventually end up getting stuck in this weird cycle, but maybe for the 1940s this was good enough. Maybe they only needed a few random numbers, and this was good enough for their purposes. Now, we could improve the random number generator a bit. We could do something like, if the number ends in 2 zeros, then maybe add 1 to it in order to get it stuck out of the cycle. But let's just stick with the pure algorithm itself. But that's the idea, is we've got this function that takes a number, it computes a result from the number and returns it, but the function itself doesn't print anything out. Its only purpose is to calculate the next number in the sequence. And then main will take care of calling that several times in a row in order to produce this whole sequence. So let's just write the last little piece of this program, which is to prompt the user to type in the seed, and then obviously the seed should not be a negative number. So let's call this int get seed. So we'll prompt the user, please enter the starting seed value. And then we'll do a, we need a variable. So let's go int s. Scanf %d comma ampersand s, didn't forget this time. And then we could just return s. And then down here in main, instead of just saying int s equals 4523, we could say int s equals get seed. So we'll call get seed, and whatever value it returns is going to be used by main. So let's compile this and run it. Enter the seed value. Let's just type in, I don't know, 1235. And then it produces our sequence. So our loop is just going until it hits 100 iterations. If you're applying this to the Collatz assignment, then you should stop the sequence when you hit 1. So as soon as you see a 1, then you're done at that point. Now, one thing that my get seed doesn't do that you will need to do is this one accepts any number I type in. Your starting, get start function should make sure that the value that it returns is going to be a positive number. So there should be a loop in here to make sure that the user types in a positive number. If the number is negative or 0, then it should loop back and reprompt the user over and over again until they get a value that's positive. Okay, so this is a simple example of a random number generator from back in the 1940s that was good enough for computers back then, but it's obviously too simple for what we would need for today. Today, the same concept still applies. You've got this seed number that's used to kick off the calculations, but the calculation it does is a little more complicated. It's actually not that more complicated. It's a simple multiply and an add and then a divide at the end. But they use bigger numbers, and if you choose the numbers well, then you can produce nice long sequences of numbers, random numbers. And the formula for doing random number generators these days is not complicated because it has to be fast. you're playing something like a game or you're doing a simulation of physical processes, you need lots of random numbers really fast. And so you want the random number generator to be fast and produce numbers that are good enough for your purposes. They aren't perfectly random, but they're good enough. Okay, so that's a overview of the 3 programs you're writing this week. Any questions on that? Okay, I want to leave you for the next 5 minutes with some kind of fun stuff. But hopefully it'll help illuminate, again, some unique things about the C programming language. So in our program, we have this number 100 here, which is the number of iterations that we're going to do. Most textbooks and other people would tell you, you shouldn't have a number like that sitting in your program. You should make that be a constant up at the top of your program so that you can change that later on. If I only want to do 50 iterations or I want to do 1,000 iterations, all I have to do is change that one constant at the top of the program, and I don't have to hunt through the program to go and find where it actually is. So let's replace this with a constant. Now in C, the convention is constants should have names that are all capitalized, and that's just there to make it stand out, easier to see. So let's put like max IETR, max iterations, in all caps, and then at the top there's a couple of different ways we can do this. We can use a preprocessor define, and this is the way your textbook probably does it, and most textbooks will do it. And this statement here is actually a preprocessor directive. This is not a piece of C code. And it says, define this symbol or this name called maxiter and give it the value 100. And so what the preprocessor now is going to do is everywhere where it sees maxiter, it's just going to swap in the value 100. Okay, so it's literally going to do a search and replace. So it's going to search for maxiter and replace it with 100. So when it comes down to here, once the preprocessor has done its work, the word maxiter is no longer in the code. What's there is the number 100. In fact, if I go ahead and save this, and then I run the compiler to show it the output of the preprocessor, oops, not C, it's capital E, then we can see in the preprocessed C code that the number 100 is sitting there. So it actually took the value of maxiter and swapped in the number 100. Another way to say it is by the time it gets to the compiler has no idea that there used to be a word sitting there. Now there's just a number.
Is it somehow better that it's not in C and it's like, yeah.
Yes and no. Is it better? Like is it better that this one number 100 is here? So if it was like a variable, if I did int maxiter equals 100, then when I run the preprocessor, we can see that now maxiter is still sitting there. The number 100 is not sitting there. And so when it generates the code, then there's going to be the number 100 stored in a memory location. And when it has to go and look at the maximum value of this loop, it's going to go have to retrieve that number.
Oh, okay.
And then plug it in. Okay, well, at least that's conceptually what's happening. In reality, the compilers these days, the ones from 2022, are so good that they're going to see that although you assigned it to a variable, you never actually changed the value of that variable anywhere in your program. And so the compiler is going to say, although it's declared to be a variable, it's actually a constant. And the compiled code will no longer have maxiter sitting there. The number 100 will be sitting there in the compiled code. if we were to look at the actual assembly code that gets produced, the number 100, the number 100 will be sitting there.
Does Clang do that or not?
Yes.
It does. Okay.
Yeah. So Clang it analyzes your program and sees that although you created it as a variable, you never changed it anywhere, and so it's really just a constant. Now, you can give the program a hint that it's a constant by putting the word const out in front. And now you're telling it, you're doing two things. One is you're telling it, for sure, this is a constant. But also, you're now telling the compiler, don't let me ever attempt to change that value. Right? It'll throw an error if I attempt now to change this variable, because I've told it it's a constant. In the other version I had, where I didn't have the word constant there, I could have changed it. And then the compiler would say, oh, now it's a real variable, and so now I'm going to have to go look up the value every single time. But by putting the word const in front, it now knows I'm never going to change this value, and it will forbid me from doing so. So there's some additional checking that's happening to make sure that I don't change it. However, when I compile the program, or at least run it through the preprocessor, there's still max iter sitting there, but the C compiler, the next phase, is going to see that it's declared to be const and will swap in the number 100. Okay, so the define just kind of like, define versus const is just changing where in the pipeline is that number 100 going to be stuck into the code. If you do it as a define, it's going to be stuck in at the preprocessor level. If you do it as a const, it's going to stuck in at the compiler level. But eventually, the number 100 will just be stuck there. So, like, what's the difference? Like, why would you use one over the other? So, if you use a define, it's literally doing a search and replace. Everywhere where it sees max iter, it's just going to swap in the number 100. And that could potentially mean you might end up with nonsensical programs if you do that. Like, let me put it back as a define. Okay, so I could put in max iter somewhere else. Like, I could put it, let me find a place to put it. Let me just stick it right there. So when I run it through the preprocessor, you can see that number 100 got stuck there, and now I have this nonsensical mathematical expression, which is going to throw an error at me. So it says, hey, you know, there's a problem here, or we know what's going on. And then now you got to go and figure out what happened. So the define literally allows me to stick the number 100 wherever I want in my program, whether it makes sense or not. And this could potentially create problems later on down the line, because since it's just doing the search and replace, you might end up with C code that doesn't resemble what you thought you wrote. Right? You see this error message and you're going, that's not what I wrote. That's because the preprocessor went and stuck in this other stuff for you. So by making it a constant integer max iter 100, we tell the compiler that this is a constant, its value is 100, and because it's an integer, it has a type associated with it. And that means that we can only use this constant where an integer would be appropriate to use. Okay? So it means that I can't just stick max iter in anywhere willy-nilly, because now that'll generate a type error. It'll say, hey, well, we got an integer here. I expected, let's say, a string, and that's a problem. Okay, so by making it a constant with a type, the compiler can now do type checking on that constant and throw you errors that are more appropriate, perhaps, to that situation. Declaring constants is a little bit of a more modern C construct. They didn't exist in the prior version, really old versions of C, and so a lot of textbooks and a lot of reference materials still use the define method for declaring constants, because it's going to work for any version of the compiler you use. Whereas using constants is going to be more dependent upon using a slightly more modern compiler. Okay, but you can take this and just go totally crazy with it. Like, let me do define P to be printf. So now everywhere where it sees the capital P, it's just going to swap in printf. Right? Because it's literally just doing copy and paste, or not copy and paste, search and replace. So if I run it through the preprocessor, we can see that everywhere where I had P, it just swapped in printf. And I can go define S to be scanf. And I can do wacky stuff like define, and it doesn't have to be capital letters, it could be lowercase letters too. I could define PP as being plus plus. And then down here, I could put in PP, but now IPP looks like a variable name, so just to differentiate it, I'll put a space in there. But then when I compile this, or not compile it, but run it through the preprocessor, we can see that the PP has been replaced by plus plus. I can make my own keywords. I can make it so that everywhere where I see the word float, it's going to swap in the word int. How's this for crazy, right? Now it appears like your program runs entirely on floats. I mean, what else could I do? And then maybe I can just go totally crazy. I keep hitting enter instead of shift. So at this point I want to find out, does this compile? Whoops, I'm missing. Oh, that should have been an underscore. Where was that? Here. Okay, still compiles, still runs. I entered 1,000. That should have been 1, 2, 3, 5. Still runs. Good. Yeah, I'm essentially creating a whole new programming language just by using defines.
That's so wacky.
Do you understand this program anymore? Does it still compile? Oops. Sure does. So, debug that. Does it still compile? Absolutely. So because you're taking advantage of the fact that the preprocessor just simply looks for that string and then swaps in the other string, you can almost like completely hide what your program actually does. Make it impossible, almost impossible for somebody to figure out what it does. Now all they have to do really is just run the preprocessor on it and then see the resulting C code, and then they can get the original program back. But that's kind of like a technique that some people use to hide what their program actually does, so that upon kind of casual inspection, it just looks like random characters. And in fact, there is a whole contest out there. The International Obfuscated C Code Contest. Obfuscation means to hide its true purpose. And it's been going on for decades, but if you look at like some of the earlier ones, no, not that one. How about this one here? You know, what does that program do? Well, compile it and run it. Here's these techniques, right? Defining these various strings that all look very similar to each other to be parts of the program, and then you end up with this absolute mess.
Is this how people made that like that one C program that was like an animated like 3D donut, but it like but the actual code was in the shape of a donut?
Yeah.
Okay.
Yeah. So some people take this obfuscated C code contest as kind of like a challenge to make what you might call programming poetry. Now take a step back and blur your eyes. What is that?
Train.
It's a train.
I thought it was a snail at first for some reason.
So one of the goals of this contest is to create your submission and then try to fool the judges. So are the judges able to figure out what your program does without actually running it? These days there are other contests called code golf contests, which is to make your program do a specific task, but in as few characters as possible. So you're trying to write the shortest program possible to make it do a particular task. Kind of like in golf, where the goal of golf is to get the lowest score possible. And so you're trying to basically remove any character you don't need from your program. You make your function call names as short as possible. You omit syntax if it's not absolutely necessary, and you try to just strip out every single character you possibly can. This program's great, right? Because every line is basically a mirror image of every other line. Does this program actually run? Yeah. You can take this program, copy it, paste it into your editor, compile it, and run it. And now, with one caveat, a lot of these entries were written back in the 80s and 90s when the C compilers were running older versions, older standard versions of C at that time. Newer compilers are running on a different standard, so they might be using C99 or C11 or even C20. And some of those standards have additional restrictions on what you can and can't do. So, for example, earlier versions of the C compiler made it kind of optional to put what type a variable was. You could just simply declare a variable, and if you didn't tell it what type it would just assume int. It was an implicit assumption that it was an int. Later versions of the compiler require you to put the type there. So even if it's going to be an int, you still have to put the word int. So that means some of these earlier entries don't work on the newer compilers because they might have omitted that word int when it wasn't absolutely necessary. And so you kind of have to go and maybe fix them or go and find older versions of the compiler and run them on these older versions of the program, these older entries. But for the most part, they should work. All right, so what I started with there was what's the difference between constant integers and defines. Hopefully you got a little bit of insight into why you might use one over the other. And it has to do really with type checking and not allowing you to write syntactically incorrect programs. Defines might allow you to do that, and they don't have type checking. And the constants do have the type checking, and they're also syntax checked, whereas the defines are not.
If you use that constant int in the beginning of the file, what's the scope of that? Does that become available to other files that you include in the project?
Well, I lied to you a little bit and said that function names and globals are completely global to your whole program. They're actually just global to your file. So there's really kind of three scopes, right? There's local variables that are local to a function. There's global variables, which are global to the file in which they are defined. And then there are like true globals, which sit outside and it can be access to all of them. And what you have to do there is you have to declare the variable in one file, and then in the other files that access it, you have to declare it as being extern, E-X-T-E-R-N, which tells the compiler, here's a variable name, its true declaration is somewhere else. But at least here's the name of it, and it knows that it can access it. And that's how you make true globals. So you define it in one file, and everyone that wants to access it, you say extern, and then it can access those in other files. So you still have the problem where function names have to be unique across all your files that are being compiled. But things like variable names are local to the file in which they're declared.
Okay, thank you.
And so that means that you can write a chunk of a program and use what looks like a global, and it won't interfere with other people's globals. Okay, so that's it for today. Next time, I don't remember what we're getting into next time. Actually, I was only thinking one week ahead, so I knew we were going to do functions this week, and then I'll look in the modules list and we can see what we're doing next week. Let me look at it here. What are we doing next week? We are done with level 2. Oh, we're working on arrays. So we'll learn that arrays in C are similar to Java. The syntax looks very similar, but the way you create the arrays is different. A little bit different. Different in a good way, because it's actually easier. So we'll probably spend a day or two on arrays, and then we're moving on to more complex arrays, and then to really, by the time we get to week 5 or 6, we're moving into pointers, which is now where you're going to really get into different stuff that is unique to C that Java doesn't have. Okay. So I hope you all have a great weekend. Get started on these programs as soon as you can. Let's see. Oh, there was a question from someone who said they had a question about the flag program. Why don't you go ahead and ask your question.
Oh, well, I don't know the exact question to ask. Is it possible I could just share you my screen? You kind of see what I have.
Why don't we end the recordings here, and then we'll go ahead and do that. Okay? So just give me a moment here, and I'll just say, hope you have a good weekend, and get started on these programs. If you have any questions, there's the Discord chat, there's the discussion boards on Canvas, and there's also all of our student assistants and tutors that can help out as well. So take care, have a good weekend, and I will see you later. Bye-bye.
Thank you.
Recording stopped.
And then the YouTube folks, I will see you as well next week. So we'll be back on Tuesday and Thursday talking about arrays, and then on Monday and Wednesday in my discrete structures course, we're talking about Boolean logic, gates, and circuits, and how the fundamental building blocks of a computer are used to be, you can put those together and build a working computer out of that. So that'll be fun. So I look forward to that. So again, goodbye all you YouTubers, and I will see you later.